This figure shows two blocks of masses 2 kilograms denoted by small m and 3 kilograms denoted by capital M. They are connected by a rope of negligible mass. A force F of magnitude 30 newtons is applied to mass small m at an angle theta, which is 15 degrees below the horizontal. The coefficient of kinetic friction between the floor and each block is 0.3, denoted by mu k. Then we are asked to find the magnitude of the acceleration of the blocks and the tension in the rope. Okay, let's begin to solve this problem. Here we are given small m as 2 kilograms, capital M as 3 kilograms, magnitude of force F as 30 newtons, angle theta as 15 degrees, and mu k as 0.3. To solve part A, we draw the free body diagram of the whole system. Two masses and the rope as a whole are considered to be a single point-like particle. Then it is convenient to represent the surface by the x-axis and the straight line perpendicular to the surface by the y-axis. We draw all the external forces relevant to whole motion. As natural, we begin to draw the gravitational force acting on the total system. It is in the downward direction, that is, negative y direction. Since the total mass of the system is small m plus capital M, then the gravitational force is gravitational vector G multiplied by small m plus capital M. The common mistake made by many students is to take the magnitude of the normal force as only the magnitude of this gravitational force. But wait a minute. In this configuration, since external force F has components on both axes, before determining N, we draw vector F. And we write angle theta here. The next step is to decompose vector F onto the x-axis, which is F times cosine theta, and on the y-axis as F times sine theta. Now we are ready to determine the normal force. It is outward from the surface, namely, it is in the positive y direction. Its magnitude is nothing but the magnitude of the net force in the opposite direction, that is, negative y direction. Then it is calculated to be N equals small m plus capital M times G plus F times sine theta. So we can determine the kinetic frictional force by the following formula. Small f k equals mu k times N, and put the equivalence of N into here. Then we get mu k times small m plus capital M times G plus F times sine theta. Here we have only F times cosine theta, which is in the positive x direction. Then the kinetic frictional force Fk is antiparallel to that force. Namely, in the negative x-axis. Well, it is time to find the acceleration of the blocks. We consult the Newton's second law, which is F net equals mass times acceleration vector. In our case, the motion is only in the x-axis. Therefore, the net force is F times cosine theta minus small f k, which is equal to total mass, that is small m plus capital M times acceleration a. Before putting all the numerical values into this formula, we recommend you to find an expression for a. Thus, if we divide both sides by small m plus capital M, we get a smart formula for a as a equals 1 over small m plus capital M times f times cosine theta minus mu k times small m plus capital M times g plus f times sine theta. Now, we put the corresponding numerical values for these quantities into this equation to get a equals 1 over 2 kilograms plus 3 kilograms times 30 newtons times cosine of angle 15 degrees minus 0.3 times 2 kilograms plus 3 kilograms times 9.80 meter per second squared plus 30 newtons times sine of angle 15 degrees. And the result in your calculator will show you 2.389 meter per second squared. And the result is approximately 2.39 meter per second squared. Note that in the intermediate step, we have written the result in 5 digits, which will be used in the following calculations, and again the final result is in 3 digits. Okay, let's solve the second part. In this part, we are asked to find the tension in the rope. The tension acts on each body separately. The magnitude is distributed uniformly in the rope. So we can calculate it by analyzing the forces acting on one of the two masses. The number of forces acting on capital M is less than the number of forces acting on small m. Therefore, it is convenient to analyze capital M. We draw the free body diagram of capital M. We represent it by a point. The axes are drawn like this. The first external force is the gravitational force acting on capital M, which is gravitational acceleration vector g multiplied by capital M. The second external force is now the tension force to the right, and let's denote it by capital T. Normal force N prime is calculated to be capital M times G. It is in the positive y direction. Then the kinetic frictional force Fk prime is found to be mu k times M prime, which is equal to mu k times capital M times G. To find tension T, we utilize the Newton's second law, that is F net equals M times A. The motion is in the positive x-axis, as we have found in the first part. Thus, we write t minus fk prime equals capital M times acceleration of the whole motion, that is a. First, we find an expression for t as t equals capital M times a plus fk prime, or substituting fk prime, which is mu k times capital M times g, we obtain capital M times a plus mu k times g. Next, substitute the corresponding numerical values into this equation to get t equals 3 kilograms times 2.3897 meter per second squared plus 0.3 times 9.80 meter per second squared. Then the result is approximately 16 newtons, which is also in 3 digits. Okay, this is the end of the solution of this problem, and let's have a look at the fifth problem.